Hi, I'm Darren and welcome to Level Up Double E Lab. I've got nothing on my workbench today. That's because my project is outside. Let's check it out. When it comes to putting up my various ideas for amateur radio antennas, I've been fortunate. I own my own home with a small but workable backyard here in the burbs, and most of all, I've got no HOA. My more recent ideas have been built around this 30-foot tall telescoping steel mast. I've used it for various dipoles, but my current obsession is a classic end-fed half-wave antenna. It's the kit that's available from ARRL. I trimmed it for use down to the 40-meter band and got lucky. It barely fits in my backyard. The far end of it is held up by a 10-foot dock pole clamped to the fence post in the corner. Now, end-fed antennas have an impedance that's much higher than dipoles, so they need to have a transformer at the feed point. The ARRL kit comes with a really nice 49:1 transformer design that's not too difficult to build, and it comes with a decently rugged plastic box. Let's back up a bit and talk about suspended wire antennas in general, starting with the dipole. This is typically the first antenna that novice hams will build, and I certainly did back in the day. It's simple, easy to construct, and its behavior is well defined and predictable. It's also usable on odd multiples of its fundamental frequency. So, for example, a dipole size for transmission on the amateur 40-meter band is typically usable on the 15-meter band because 21 MHz is 3 times 7 MHz. An obvious requirement for the dipole is you need 2 tall objects to string it between. I'm showing here a couple of trees, but virtually anything high enough off the ground will work. But what if you only have one really tall object? Let's say it's a metal pole attached to your house. Well, the dipole doesn't have to be straight. In fact, you can slope its ends down towards the ground and anchor it to some short poles and make what's called an inverted V dipole. It's a good solution for this situation, but it does have some compromises as compared to the straight dipole. Alright, but what if you have a situation like I do? A single really tall object at your house, but only enough room in one direction to stretch out a long antenna. Now you get into options like an off-center fed dipole, a random wire antenna, and the end-fed half-wave antenna, or EFHW. At first glance, it seems like an ideal solution. Just run your feed coax to the top of the tall object and attach it to a single wire running down to the far end of your yard. But not surprisingly, the devil, as always, is in the details. And the first of those details is this. There's a huge impedance mismatch at the junction of the feed line to the antenna. Now, one of the advantages of the dipole is the impedance at the center feed point is about 73 ohms, depending on its height above the ground. And 73 ohms is close enough to the 50 ohm impedance of typical coax that you can generally get away with soldering the center conductor of your coax to one side of the dipole, the braid to the other side, hoist it in the air, and get transmitting right away. The EFHW, on the other hand, has very high impedance at the feed point, generally around 2500 ohms or possibly higher. If you tried to feed it directly with your coax, your transmitter would see an unacceptably high SWR. Not good. To avoid this, an EFHW has a transformer at the feed point, typically a 49:1 impedance ratio, which you can get from a 7:1 turns ratio. And that's exactly what's in the ARRL design that I showed earlier. There's 2 turns on the primary and 14 turns on the secondary. Okay, so we've got the impedance match close enough. The next detail with the EFHW is the counterpoise. So what is that? Well, simply put, the counterpoise is the other half of the RF circuit, the companion to the long wire portion of the antenna. Now, I'm really tiptoeing here around what should be a more detailed RF theory explanation, which would be over my head anyway, so just roll with me. What I find interesting is the EFHW will always try to use something as the counterpoise. You can attach a dedicated counterpoise wire, which is typically pretty short, around 5% of the longest wavelength you're transmitting, which in my case works out to around 6 feet or so. But if you don't attach anything, then the antenna will seek out and use something else, typically your coax feed line or maybe a nearby metal object like your tall pole. Now, some hams do get away with using the coax as the counterpoise, but sometimes doing that can put so much RF on the coax that it makes its way back into the shack. And that's exactly the problem I'm having. Whenever I tune the antenna for the 40 meter band, every time I key the mic, the LED light above my desk would randomly turn on and off. That's not good. In fact, that's unacceptable. There's also a second problem with my antenna. The SWR is not acceptable on 3 of the 4 bands. Here's what the starting conditions look like. I'll go into more detail shortly for how I got this data set, but the quick takeaway for now is only the 20 meter band looks good. The other 3 have high SWR and SWR minima outside the band or both. So I've got some work to do here as well. It's very tempting at this point to start trimming the antenna length to optimize the SWR. And if this were just a basic dipole strung between 2 trees high off the ground, I might do just that. But I'm going to tackle the stray RF problem first, and to do so, I'm going to use a very common solution. I'm going to insert a common mode choke at the antenna feed point. Now that means the coax can no longer act as the counterpoise, so I'm also going to add a separate wire as a dedicated counterpoise. Now making these changes might change the tuning of the antenna, which could then shift the SWR minima. So it makes sense to make these changes first and then optimize for SWR next. Okay, so what is a common mode choke as used with coax antenna feed lines? Well, very simply, it's a specifically constructed inductor that significantly reduces any RF currents that are trying to flow in the same direction on the shield and center conductor, while not adversely affecting the RF currents flowing in opposite directions. Those opposite currents are better described as differential currents, and they are what's normally flowing between the transmitter and the antenna. The same direction currents result from the antenna trying to use the coax as the counterpoise. Now, this is a big simplification, but good enough to move on. I've got a few options here as to where to put this choke. Option number 1 is to put it right at the antenna feed point. If I do that, I'll need to add the dedicated counterpoise wire I mentioned earlier. That's easy enough to do. There's a terminal already present on the ARRL box to attach it. Option number 2 is to put the choke about 6 feet or so from the antenna feed point, which lets that 6-foot section of coax function as the counterpoise. I don't have a preference right now, so I'm going to experiment with both ideas. Okay, so here's the common mode choke that I built. No need to reinvent the wheel here. This is a very common design found all over the internet. It's an FT240 43 core with 12 turns of coax wound in a very specific pattern that causes any common mode current to induce opposite polarity magnetic fields in the core, which creates the desired high impedance. But before I put it up in the air, let's find out how well it works. First, let's look at the insertion loss. I measured this by connecting the choke the normal way to the ports of my Nano VNA. And as expected, the insertion loss is very low, less than half of a dB. Now that's in the ballpark for the expected loss in the 3 feet or so of coax if it were just laying on the workbench, showing that this design won't adversely attenuate the signal we're trying to get to the antenna. Now, to measure how it performs under common mode conditions, I'll first need to make a special fixture that shorts the shield to the center conductor at both ends. That'll force the test to use almost all common mode current. I've also shorted the outer shields together at the SMA connectors. Now, that probably isn't necessary, and worst case, my data might underreport the performance. And here are the results. The attenuation exceeds 30 dB from around 3 MHz to 17 MHz. Pretty good. The drop-off as frequency increases is expected. It's likely the stray capacitances in the windings and the coax itself are starting to dominate, but still, minus 30 dB is likely to work very well. And just for kicks, I measured a 3-foot length of RG59 that I had laying around just to show how much more effective the choke is. So at this point, I'm ready to do a bunch of antenna experiments, but let's first take a quick look at how I'm going to collect all that data. I'll make all the measurements here at the transmitter end of the feed line using my Nano VNA with the Nano VNA Saver software. Now, regarding the data collection, using the Nano by itself will only give you around 101 data points per scan, which is not the greatest resolution over the whole HF frequency spectrum, but the software lets you do a sequence of sweeps, and that's what I did. I set it to take 20 sweeps from 1 MHz to 30 MHz, which gives me about 2,000 data points with a step size of about 14 kHz. Okay, first change. Let's see what happens when I add the common mode choke at the antenna feed point. It's not exactly at the 49:1 transformer box. There's about a 6-inch coax pigtail between them, but that's definitely close enough. Scan number 6 is that result, and scan number 1 is the initial condition. Now pay no attention to the order of these scan numbers. I kinda jumped around here with ideas, and now in hindsight, I'm trying to go through all this data in a more logical order. Anyway, the results look pretty bad. The overall response changed dramatically. There's no indication of resonance anymore on either the 40 meter or 20 meter bands. 10 meters looks better, but whoopee. I wasn't seriously considering using the antenna this way. After all, there's no intentional counterpoise here, so the system might be just using the mast or the nearby rain gutter as the counterpoise. But this does show that the choke definitely had an effect. Now let's try a couple more ideas here. Scan number 5 keeps the choke at the feed point and adds a counterpoise wire parallel to the feed line. Scan number 8 does not add the counterpoise wire, but it does move the choke about 6 feet away from the antenna feed point, so that short segment of the feed line can then act as the counterpoise. These are the options that I mentioned earlier. Let's look at the results by band. For 40 meters, the minima now reaches down almost to an SWR of 1:1, but the frequency has shifted lower by about 150 kHz, which is going in the wrong direction. 20 meters hasn't moved much from the starting condition. 15 meters, well, that just stinks worse. And 10 meters actually looks encouraging for scan number 5, the one with the dedicated counterpoise. Now, these results lead me to think that adding the counterpoise wire is likely directionally correct, but routing it parallel to the coax is not the only way to route it, and it concerns me that doing it that way might accidentally couple RF back into the feed line and partially negate the effect of my choke. I've got 2 additional options within the physical constraints of my backyard. For scan number 7, I can stretch the counterpoise out using some paracord hooked up to another dock pole that's in the southeast corner of my yard. That puts it at about 90 degrees to the antenna, which slopes downward to the southwest. For scan number 9, I can stretch the counterpoise out to yet another dock pole. This one is directly east of my house, and that would put the counterpoise at about 150 degrees to the antenna. Well, here are those results, and they're almost identical to each other. On 40 meters, I've gained back some of that frequency shift. 20 meters has shifted down a bit, but still looks good, and little change on 15 and 10. So of all of these experiments, I like number 7 the best. That gives me the common mode choke at the antenna feed point that I need, and stretching the counterpoise at 90 degrees to my southeast dock pole is preferred because I'd like to use my east dock pole for a future antenna. Now I can look at optimizing the SWR minima, but here's a new problem. The main antenna is 65 feet 7 inches long, which should have a fundamental resonance at about 7.13 megahertz, but it's not performing that way. It's at 6.8 megahertz, 330 kilohertz, or about 5% too low. If I were to trim the length by 5% to get it to resonate at 7.13 megahertz, then all of the harmonic resonances would be expected to increase by 5% as well, which would be disastrous. The second harmonic would be at 14.8 megahertz, which is well outside the 20 meter band, and so on. So why is the 40 meter SWR minimum so off as compared to the other bands? Well, after quite a bit of online research and a bit of AI input, What I think is most likely happening here is my metal mast and dock poles are adding capacitive coupling at the ends of the main antenna, which is artificially lengthening it. The antenna barely fits between those two structures. The endpoints are less than a foot away from them. I cannot replace them with insulated poles, nor can I stretch them further apart, so I'm stuck with their effects. But there is something I can attempt here that would make the antenna appear shorter on the 40-meter band while mostly not affecting the higher frequencies. Back to the simple illustration. What if I put a capacitor and an inductor in parallel right at the point where I want to trim the antenna for 40 meters? Recall from basic electronics that a paired capacitor and inductor will have a fundamental resonant frequency, and if you put them in parallel, they'll have a very high impedance at that frequency, or essentially an open circuit. But away from that frequency, they allow AC signals to pass through. Hey, that's brilliant! So at 40 meters, I can make the impedance matching transformer only see this much of the antenna, while for all the other frequencies, it'll see the entire antenna. And this will happen automatically. I won't need to manually do anything. Now, this type of antenna is well known in amateur radio. It's called a trap antenna. It's commonly used in multiband dipoles, but the way I'm thinking of using this trap is a bit different here. Typically, you'd use traps to shrink the antenna effective length as you go up in frequency. Here, I'm doing the opposite, lengthening it as I go up in frequency. But I think the physics will still work in my favor. And for the second time on this project, I'm not gonna reinvent the wheel when I construct this trap. A very common technique for us hams is to build them from a length of coax wound on a cylindrical form. The geometry of the windings plus the specific way you connect the coax center conductor and shield will provide the necessary capacitance and inductance to make the resonant circuit. In fact, here's a very handy online coax trap calculator provided by wireantennas.co.uk. I just so happen to have a chunk of 1.5" PVC pipe and a bit of high-flex RG8X laying around. So I set the resonant frequency to the middle of the 40-meter band, and the calculator spit out the various winding parameters. Looks like I need just over 10 turns of coax. Jumping ahead a few hours, here's the finished trap. I made the end terminations from 14-gauge solid copper wire with some ring terminals crimped and soldered just for good measure. Inside the pipe, well, it's a bit ugly. It's not easy to reach and solder those conductor and braid connections in the pattern that's needed because the access is pretty limited. And just like I did with my common mode choke, I want to test the performance of this trap before I put it up in the air. Here's the data taken on the Nano VNA. I had to improvise connections to the ring terminals, so the magnitude of the insertion loss might be off a bit, but I really don't care. I mostly just want to confirm that the resonant frequency is in the right place and to see what the profile around it looks like. And I think this data is pretty good. Resonance is happening in the 40-meter band, and the attenuation on the higher bands is actually less than the attenuation at 80 meters. I'll take that as a positive sign. That's telling me this trap is likely to not work worse on those higher frequencies than it would on its usual application on the lower frequency 80-meter band. So with the data looking good, I finished prepping the trap, which included trying to put some sealant on the internal soldered connections. Yeah, that did not go very well. The silicone caulk seemed to react with the copper, maybe because of an acetic acid cure. I also connected up a pigtail to one end. This is the final version after I did some trials with a longer pigtail and a longer main antenna, and did several rounds of trimming and scans to dial in the SWR minimums. And here's the final result as compared to where I started, 14 scans later. I skipped over some of the scans where I was playing around with doing the VNA calibration at the antenna end of the feed line. That just did not give me anything useful. Anyway, the added trap did exactly what I intended. It effectively shortened the antenna just for 40 meters. So now I have beautiful SWR readings across the majority of the 40 meter, 20 meter, and 10 meter bands. 15 meters, well, that's still a dog's breakfast though. I'm out of ideas for the moment of what to do with it. But regardless, I consider this effort a major victory. Getting good SWR readings is certainly an important part of tuning an antenna, but most important is just how well does it receive and transmit. Do I have a winner here, or do I have a glorified dummy load hanging over my backyard? Well, my timing for working on this project could not have been better. This past weekend was the annual ARRL Field Day event, which is where thousands of my fellow hams will set up temporary stations with the goal of demonstrating emergency preparedness. So it was a great opportunity for me to make lots of contacts. So I connected this new antenna to my FT450D 100 watt transceiver and I went to town. After operating for about 6 hours on Saturday and 2 hours on Sunday, I managed to log 114 contacts. And looking at which state those occurred and which frequencies they occurred gives me some initial insight as to just how well the antenna is working. And here's what the data looks like. 20 meters was a big success. I made 66 contacts in 34 states, including Hawaii. I also picked up a few Canadian provinces. Overall coverage was essentially coast to coast. The SWR reported by my 450D concurred with my VNA scans. It was 1.2 or lower for the entire phone portion of the band. And since I used 20 meters a lot, I'm very happy with this performance. Downshifting to 40 meters, I managed to make 29 contacts here, which added 6 more states, bringing my total to 40. Interestingly, all of my QSOs were southeast of my location. Now I wonder if 40 meters has a main lobe pointing that way and a reduced lobe going to the northwest. It also might have just been the band conditions over the weekend. And regarding SWR, it was definitely higher than at 20 meters, but it never went above 2 and I did not need to use the built-in tuner on the 450D to compensate. But most significantly, the stray RF problem I was having earlier is gone. Not once did that LED light over my desk flicker off. So that common mode choke and added counterpoise appear to be doing their jobs nicely. Here's a bonus. I was actually able to make 4 contacts on 15 meters. It took extra effort though. The 450D wouldn't key up without using its auto tuner. But since I have to retune it with each change in frequency, it's not very practical. Lastly, 10 meters. Here I made 15 contacts, and just like for 40 meters, they were all to the southeast. I stayed around 28.3 to 28.5 megahertz, which is well within the minimum of the SWR that I saw in the VNA, and the 450D was quite happy working with that. Bottom line, I'm now loving the performance of my end-fed half-wave antenna. And I will do some digital mode QSOs like FT8 on it in the near future, and then use the Internet Reception Reports feedback to get a better idea of the consistency of the radiation pattern and see just how much it varies over time and over band conditions. Now, using a trap like I did here to artificially lengthen an antenna might seem a bit crazy, but as the saying goes, it ain't crazy if it works, and in this case, it seems to be working just fine. Now, I hope you guys enjoyed this short episode on this end-fed half-wave antenna, and I hope you're still enjoying the content and the variety of projects that I do here on my channel. So until next time, bye for now.